your questions were about the rational roots theorem. What does it actually look like in practice? What does it really mean? And then thinking a little bit more about what is density and what are the ramifications of density. And the question about density is one that we're going to thread throughout the whole first half of our semester. Density is a major, major concept. And so I wanted us to be exposed to it first, even though we won't be able to prove it yet. We'll probably be until packet 3, no, maybe even packet 4, before we're able to actually prove that the rational numbers are dense inside the real numbers. So we'll talk more about density on Wednesday. But for the sake of today, let's think about the rational roots theorem a little bit more. So the big task that's sort of first for us is to be able to take a number which we sort of think is a real number, even though we don't really know what real numbers are yet, and that's really the majority of the story of our course is what are the real numbers, really? Where do they come from? How do they work? How do we think about them constructively? Where do they come from? But if we take a number that we sort of understand is a real number based on our history, a number like the number x, which is the square root of radical 2 minus 1, okay, then the question is, how do I know whether that number is rational or irrational? So that's the big first question. How do we know which side of that line, which side of that divider to place this number on? So there are some ways of determining whether a number is rational based on techniques from other courses like number theory. Like you've probably at some point seen a proof for why the square root of 2 is not a rational number. Right? And it involved a proof by contradiction. Assume that it is rational and then derive some contradiction based on the evenness and oddness of two sides of an equation, each of which is an integer. It's the kind of proof that you probably saw in Math 180. If you took number theory, you probably saw it again in those contexts. For a lot of math majors, it surfaces as one of their favorite proofs. It's the one that has a lot of staying power because it's got this really nifty argument to it. But the tack we're going to take on is a little bit more powerful, although it requires us to use the more powerful tool of the rational roots theorem. So I want to kind of illustrate it with a different example than the one that's up here to kind of inspire you for how an example like this one might work. I'm going to sketch an outline for how to use this kind of reasoning to prove that the square root of 2 is not rational. So square root of 2 is not rational. Here's kind of a 3-step argument for how we might prove that. The first step is, what do we even mean by the square root of 2? What is the square root of 2? A lot of ways to think about what the square root of 2 is, but the one that we're going to hang on to is we're going to think of this number as the root, or a root, I should be really careful here. Think of it as a root of a polynomial, namely the polynomial x squared minus 2. It's a root of x squared minus 2. Why? Well, it's not quite an equation yet. What belongs on the other side of the equal sign? Yeah, exactly. When we say root, that means it makes that polynomial's value equal to 0, right? So this is the correspondence that we're going to set up. For one of these numbers which we suspect is not rational, we're going to recast it as a root of some polynomial equation. And notably, this polynomial has coefficients, 1 and negative 2, which are rational. Right? So we don't need irrational numbers to define this polynomial, even though its roots may in fact be irrational. So this is a polynomial whose coefficients are rational. In fact, they're integers. And you can probably persuade yourself that if I have a polynomial with rational coefficients, I can turn it into another polynomial with integer coefficients just by clearing out all the denominators, which has the same roots. Because if I clear out the denominators, I'm not going to change the 0 on the other side of the equation. So that's the first trade-off that we make, is that we take the square root of 2, which we're just sort of writing down symbols, and we trade it out for roots of the polynomial x squared minus 2. So then the question becomes, what can we say about the roots of x squared minus 2? In particular, here's where we're going to put a fine point on it. What can the rational roots? If this polynomial does have any rational roots, what must those rational roots be? Yeah, well, that's one set of possibilities. What are the others? So they could be plus or minus 2, or they could be plus or minus 1. Now, where are you getting those plus or minus 2 and plus or minus 1 from?
Take E, just divide, what do we call it, A naught.
a naught, so that's the constant coefficient. So we're going to think of a naught as being, yeah, negative 2. Right? And so we think about what are the factors of negative 2. Well, what are the factors of negative 2? 1 and 2. But then also negative 1 and negative 2. Right? So I'll put a plus or minus in front. But then in principle, the rational roots theorem says that we also need to divide those by possible factors of the leading coefficient. Factors of 1. But luckily for us, factors of 1 are easy. And so my possible rational roots, according to the rational roots theorem, come from dividing the possible factors of the constant term by the possible factors of the leading coefficient. So that's how we use the rational roots theorem, is it takes all the rational numbers out there in the universe, of which there are countably infinitely many, and it narrows those down to only 4. These are the only 4 that could even possibly be roots of x squared minus 2. So these are the only 4 possible rational roots of x squared minus 2, but the word possible there is important. Because now our job is to convince ourselves that that number which we understand by the square root of 2 is not in fact equal to one of these. So all we have to do is persuade ourselves that none of these work. That these are not roots of x squared minus 2. How can I do that? Plug them all in. This is try them, right? We only have 4 things to plug. That shouldn't take too long, and they're nice whole numbers. So if f of x is x squared minus 2, then all I have to do is pick, for my values of x, the various values that we have. If x is equal to 1, x squared minus 2 is negative 1, which is not, in fact, equal to 0. So that means that positive 1 is not a possibility. If x is negative 1, x squared minus 2 is, again, negative 1. So negative 1 is not a possibility. And if x is plus or minus 2, x squared minus 2 is 4 minus 2, that's 2, which also is not equal to 0. So positive 2 doesn't work. If x is negative 2, it's the same story, so negative 2 doesn't work. So all we've done is we've gone down the list and we've ruled out every possible rational root of x squared minus 2. Therefore, all of the roots of x squared minus 2 are irrational. Because if one of them were rational, it would have had to have been one of these numbers, plus minus 1 or plus minus 2. And since none of those numbers work, all of the roots of x squared minus 2 are irrational. And because the square root of 2 was by definition one of those roots, that means the square root of 2 is irrational. Exactly. So there is our modus operandi for this, is that if I want to understand why one of these real numbers is not rational, I cast it as the root of some polynomial with integer coefficients. Then apply the rational roots theorem to find out what are all the possible rational roots of that polynomial. Then I just have to rule all of those out, thereby proving that our polynomial has no rational roots, and therefore our root is not rational. Now, it's worth noting that we could only do this because the square root of 2 did satisfy a polynomial with integer coefficients. Does every real number satisfy a polynomial with integer coefficients? That's a pretty loaded question, it turns out. Right? Square root of 2 does. Square root of 10 does. The cube root of 15 does. The 59th root of 125 does. Right? But what about pi? We don't think so, but it's not at all obvious how we would prove that. Right? And it is, in fact, true. Pi does not satisfy a polynomial equation with integer coefficients. It's what we call a transcendental number. Whereas numbers that do satisfy equations with integer coefficients are called algebraic numbers. And so this is a technique that will work to rule out the rationality of any algebraic number. And there are a lot of algebraic numbers in the world, but it turns out there's a lot more transcendental numbers. So even though this is going to be super powerful, it's not going to get us even close to classifying all real numbers, because the transcendental numbers are hairy.